we're going to continue adding stuff to the regression toolbox that we now started. We will discuss continuous predictors and what is called marginal effects. Let's get right into it. If you think of regression, then you're actually not thinking of taking means and you're not thinking of having categorical variables, but you're actually thinking of regression of lines, right? At least from school. So the idea is a little bit, you have this kind of regression formula here with the beta zero, like the offset here that I'm modifying here, and you have some kind of predictor and you have a slope, right? That's the whole idea. And you've seen something like that in my slides before, so it's relatively similar to what we had. And maybe this x now, if it's a continuous variable like the contrast, or it could be the luminance, or it could be the size of a saccade, or whatever, then you would have the x here on the x-axis. And then you could have like the ERP amplitude now for one time point, 170 milliseconds or something like that. And then you could try to find what is the best parameter. Here I'm just changing the beta zero. What's the best parameter to explain my data, right? And you find the best parameter that minimizes the square distance of these things. And there's some theory, y squared, etc. But just find the best line that fits the data point. And that's kind of, okay, we know from school. And then now you can do the cool bit. You go from a simple linear regression to a multiple regression. So instead of having just one x-axis, you kind of have two axes that explain the data. Maybe it's contrast and brightness. And then instead of having a single line, you have to span up a space, or you have to have a surface here, right? A plane, I think is a better word. And now you still try to find all the parameters. So you have a slope in one dimension, slope in the other dimension, and you're up and down. You have three parameters now, beta 0, 1, and 2. And you're trying to find the best plane that fits all of this. And then, of course, you could continue on, right? At some point, now I can't show it anymore because more than 3 dimensions is hard to visualize. But you could just write it up like this. You can imagine that you have n dimension, n predictors. And then conveniently, like writing all of this out, this is really bothersome, but conveniently we are now landing at this formula that we had in the very beginning, where we have this matrix product, because having this multiplications and summing all up is nothing else than doing a matrix multiplication. There's a small animation, but we don't actually care how exactly it works. Just trust me that these are exactly the same things, right? Okay, we also notice that this design matrix, and let's have a look at how they look like. So this would be for simple regression here. You get the 2 parameters, so beta, okay, should be beta 0, but well, next time you get the intercept and your slope here. And if you have multiple regression, then you just get an additional column in the design matrix and an additional parameter that you can analyze. Now, this is on one time point. We so far have always been discussing multiple time points here. So here it's now exactly the same thing. Remember, we had the single trials here, and then we had the design matrix. So now we add one column here, and we add a parameter here, and we get another effect here. Okay. So here, how we define it in Unfold would be you have this bike or stimulation condition. Or here I even have the Unfold code. The stimulation condition, and then you just add the saccade amplitude as another predictor. And now, because in stimulation in the data frame you saw the events were either strings, whether bike or phase, right? So automatically the underlying packages recognize this as a categorical variable, and here you have a numerical variable in there, and so it will automatically just put that numerical variable here in the column. Right? There's no additional logic involved here, right? And there's one more thing that I think is important to understand. These here, we were very much in ERP land. We had ERPs, we had different curves, etc. But if you have such an effect here based on a continuous predictor, suddenly this is a slope, right? Technically, this is a slope too. But this is a slope that means if I want to now later know what is now a difference of 1 degree saccade amplitude or 1 step on my brightness scale, then this would exactly be the answer. This is the answer. If I now want to know, but okay, my whole scale is from 0 to 100% brightness, what is the whole outcome? Then I would need to take this effect times 100. So scale it up, of course.
We have a quick question.
Yeah.
Does this assume exactly 1 saccade happens per trial and always at the same time? by analogy to the bike, like exactly one bike
Yeah,
appears
yeah.
per trial, and we know when it appears. So the idea of an event-related signal makes sense.
Yes. So here, basically, you can imagine that we epoch the data to the fixation onset. So 0, wherever 0 is, maybe this one here in the middle, that would be any each fixation onset. It's of course simulated data here, and we later will get to the stage where we don't even epoch. We also let the rERP do the epoching step in the design. But this is the fourth thing we will discuss. Okay, cool. Okay, so now we added one, and nobody in the world can stop us from adding yet another one, right? So now we finally we had this. Have confound control in some sense for saccade amplitude and maybe also fixation condition. Actually, in my simulation, fixation position doesn't do much, or it's less visible because maybe we have put this into pixels, and so now the max effect would be times 2000 pixels or something like that, and suddenly it's big again. Who knows, right? It's just something to keep in mind. And we will address this issue of scaling, etc., with a very clever way with the marginal effects in a second. Okay, but this is, I think, this is all you do, right? You just add continuous variable, and it will try to fit this kind of linear effects to the data. Now, yeah, I did mention that the interpretation is a little bit more difficult, and we have a really cool tool, and this also will address a question about we had earlier about the contrast coding. What is my dummy level, and how do I interpret these coefficients? And so this will address this as well. And this is making use of predictions. So what we can do if we have specified this model here, and let's say maybe the x is defined by a condition and a continuous variable, right? What we can then do, we can inspect this beta. So this is this plot ERP that you have been all doing before. Now we added this continuous predictor. So this is how it would look like. You have the intercept, you have an effect of phase versus bike, and then you have this kind of slope, right? This is relatively difficult to interpret, and maybe because basically the slope is there, because this is different to what we typically have with the ERPs. And basically the question is, how do we get from here, from having difference effects and slopes, back to ERPs that we can understand? Right. What we can do is we can do a prediction. So now we get a small hat because it's a predicted EEG data. Here we had this arrow term, right? So this is the real data, predicted data just without the arrow. And basically for each of the trials, we could back calculate what does the model think that the trial looks like, right? And this would be something like this. This is how the model thinks each trial in a certain data set here would look like. Right, so you can clearly see there's a lot of the slope effect going on here because this is the only one that has big activity here, and you can also appreciate maybe here there's a difference, etc. The scale is very much different because this is now in data space in some sense, right? We could also inspect the residuals here, but I'm not putting there because I want to focus on this prediction, because this is, well, it's interesting, but it's not particularly helpful for what we are actually interested in. So let's look closer what we are actually doing here, right? If we predict a single trial. So this is the single trial with the arrow still, but if we want to have the y hat, then it could look something like this. We have our betas, and then we put in specific values that we want to evaluate the betas at, and then we sum it all up, right? So as matrix notation, you will see in a second y, and that's okay. This should be a comma here. Sorry, not the dot dot dot. That's okay. You can write something like that, and you get for any single trial, you would get your answer. One issue is, of course, if you have many more predictors, then this suddenly gets very cumbersome, and also you can make errors. And people who have been doing fMRI analyses in SPM, they know this. They know the pain of writing your own, what's sometimes called a contrast, right? To write this contrast matrix and then counting how many zeros do I have to put so that there's one effect. Romy is saying yes, right? And I don't know how many errors in the literature are because of that. I assume there are errors because of that, because I did them myself, and it's just so easy to make a problem. So the nice thing is in Unfold, but also in other packages, there's like EM means package or the effects package in R or so, and there's an effects package in Julia as well. So we can use the effects function to just simplify this definition, and we can just say, okay, condition should be our phase condition, and my continuous variable should be 12.3 or whatever that one single trial has, right? And if you have one single trial, we could also do multiple trials, right? So multiple trials in this contrast view, you have to, for each of the trial you want to go, basically you have to build this design matrix and then evaluate it. Yeah, what we would want to do typically is actually going for multiple trials, but not the trials we've seen in the data, but like idealized trials, like perfect trials. What we can specify here would be that conditions we want phase and bike, and my continuous we want 3 variables, and then it's calculating all possible combinations of this, right? And we get an artificial new design, an artificial experimental result without any noise, perfectly balanced. Like that's what we want. That's kind of how I look at this kind of data. We want to have it balanced, right? And what the outcome of this would be something like this. So now I get 2 times 3, 6 different curves here. I plotted them at 3 different continuous values here and with the 2 different simulations. Yeah.
We have a question about how we decide which continuous levels we want to predict.
That's well, now because, given that you can do the prediction, you can just choose this is just basically interrogating the model, right? There's nothing, we are not doing any new fitting or something like this. We are simply asking the model, okay, just calculate this sum, calculate that sum. So you can start with whatever range you think could be interesting to your problem. And then, well, probably if you add 100 continuous values here, your plot will be cramped again. But we will have, in the next slide, I will also have a little bit other display with more continuous values. And then you might be able to appreciate that sometimes having a minimal set is enough. Sometimes you kind of want to have more. I guess if you have a continuous, it makes sense that continuous effects have some kind of regular spacing to it. But it does need to. You can create whatever, and it's very simple. You will also see you can easily play around, and that's exactly also what we're going to do in the next exercise with these numbers, how many you display. And the plotting library we're using is very powerful, so you should be able to even cramp in 1,000 of these lines without a problem. Yeah.
And now, can you clarify again what exactly the rERP plot shows? So they're asking phase and bike at 1, 3, and 5. What?
Okay, fair enough. So this is not a coefficient plot anymore that we had before, but this would be if you could record an EEG experiment where you, let's say, have the phase condition. So we are on the dotted lines here, on the dashed lines. And you can record it with your continuous variable, which, let's say, it's brightness levels, 1, 3, and 5. Then you could say, okay, the rERP I would get if I only have this categorical design, let's say 1, 3, 5 with phases and bikes, then this would be my 6 rERPs that I would get. So this would be for 1. This would be my rERP. I could calculate with the mean for 3. This would calculate for 5. Except that this is not what we're modeling. What we are modeling here is that we have a linear effect here. So maybe even these numbers here never actually were exactly ran in the experiment, right? Let me jump back. Oh wow, all the slides at once. Let me jump back to here. Maybe you can see here in the brightness, we could now ask for a brightness value of 60, where there was actually no single data point on this brightness value, right? So we could have the data point somewhere else than where we evaluated. And here you can see if this would be really brightness, then this is more or less randomly distributed. But now we can make it to be really like perfectly balanced in a nice regular interval, as if this would be the data we actually produced, even though we, of course, did not produce it. It's a model fit. Does that answer the question?
Yes. So we have now clarified that the 1, 3, 5 is whatever you set as your continuous predictor. That's what it is referring to.
Yeah,
yep.
Exactly. Yeah. This is now really after the fit. This has nothing really to do with what kind of events you put into the model, right? The model is fit, and now we can just interrogate it for whatever combination of parameters we want to have. And yeah, what I really enjoy about marginal effects is that sometimes you just don't care about the continuous effect. It's just there for confound control. You don't want, you basically just have two conditions like A and B. And the continuous variable might be different for A and different for B. Maybe there's like on average, because subject did larger saccades or smaller saccades or something. But you'd be interested in, well, how does my ERP look like if they would actually have exactly the same saccade amplitude, right? Something that is you could do matching or other things, but it's not so easy to say. But you kind of want to have this fixed at what we call the typical value, which is typically the mean of this predictor. And if you do that, so if I just cut out this thing and I just call the dict on condition AB, it will take the average of the predictor for all other non-specified ones, and it will give me just two curves here, right? So my marginal effect predicted Y has now two curves. Well, it's still car. I'm so close to have all the cars banned from my talks, but still struggling. But now we have two, and the continuous effect here is gone because I used for both of the curves to evaluate the average continuous value, right? And I can do the same. I could just remove the first one, don't care about the categorical predictor, but just have the continuous one. And suddenly I don't see the separation here anymore, but I just see in this case here, what is it, 10, 11 different curves, nicely delineating my linear effect. Right, so both of them are different calls, and you can just interrogate the model in all these different ways. Exactly. That you're interested in, that you're trying to understand this model better. Because now we are at the stage where you are actually going to do that yourself. I already showed you the syntax, but it's also in the notebook, of course. So now it's time to start the second notebook and do your own marginal effect, do your own continuous predictors first of all, and then your own marginal effects, and try to understand well what does it mean to have a slope or continuous predictor in your EG data in the first place. Shoot with the questions.
All right, Bene, welcome back. We have a question about syntax. Somebody's asking, what does let ... end mean? Is that so I can define the same variable again without getting errors?
Yes, exactly. I think this is the main purpose. So this is it's a local scope that you're opening that is not visible from the outside. I think that's the in Bluetooth, that's the whole thing. You notice that if you have multi-line thing, you need a begin and an end, but the variables you define in there can be visited from other cells. But if you have a let, then you can't. There's one caveat. If you change something in place, so you modify it, like you remember the exclamation mark, or you modify a column of a data frame, then Bluetooth cannot see that. So even in a let, it's not completely safe, right? So there can be some specific ways you could modify variables, and then they still mess up the whole Bluetooth system. But mostly this is, for most reasons, you just want to have a quick plot and you want to use F for figure, but F is also a formula somewhere, and then this just works.